So, did I give this theorem theorem 1, or just check what is the name that I had last time? Theorem 1? So, I guess these are the things that I said last time, right? Okay. So, we saw that suppose if we assume that 3 and 4 are true, then that would imply theorem 1, right. So, we saw that, of course. So, there was a little bit of a caveat. So, we need to also show it for pi k. So, we only showed that sigma k will belong, but let me also mention that even if you have a class for all C, that is also contained in bp.parity.c. Okay. So, this is something we left last time. So, the reason why this holds true is because the BP operator is closed under complement. Okay. So, let me elaborate on that. So, suppose if we know that this is true, okay. So, suppose there exists C is contained in bp.parity.c. So, pick a language in for all C, okay. So, the complement of that language is contained in there exists C, okay. So, since the complement is contained in there exists C, if I just switch the answers of the BP machine, okay. So, the BP machine by its definition, if an instance is in the language, it accepts with probability greater than 1 minus 1 over 2 to the power qn, and if it is not in the language, it rejects with probability that much, that same. So, even if I switch the answers at the end, it is still a BP machine, okay, which is accepting the language L complement. So, if you have any language, so for example, I mean the generalization is, if you have any complexity class C, okay, so if L belongs to BPC, so this implies that L bar will also belong to BPC, okay, and the machine is just flipping the answers. So that implies basically that part B is true given that part A is true. Okay, so right, yeah. So we saw that this follows from 3 and 4, and we saw that lemma 3 follows from the claims 5, 6 and 7. Okay, so you just switch, you just use claim 7 to switch 2 of these operators and then apply claim 5 and 6. So let us look at the proofs of the remaining statements. Okay, so let L be some language in C, okay, and define L prime to be parity L and define L double prime to be parity L prime. So then what we want to show is that L double prime is contained in parity C, and in fact what we will show is that L double prime is the same as L prime. So so X belongs to L double prime if and only if the number of certificates Y, okay, for which the pair XY is in L prime is odd. So it's congruent to 1 mod 2. This is just another way of writing it's odd. So I'll just use another notation for this predicate. In fact, I'll just so the way I'll write this is sigma, so let's call this y1, sigma over all strings y1 of the predicate L prime xy1. Okay, so let me just say what this means. So this means that this predicate, okay, so this predicate that I have, so this evaluates to 1 if this argument belongs to the language, and otherwise it evaluates to 0. Okay, so this should be odd. Okay, so now again I can expand out this predicate and write this as and xy1 belongs to L prime if over all strings y2 x comma y1 comma y2 belongs to L yeah, congruent to 1 mod 2. Okay, so now so what this says is that for every certificate y1 I have an odd number of certificates here. So basically what I am doing here is that I am taking an odd number of sums of some odd numbers. Okay, so if I just combine these certificates, I can just look at them as just one pair. So the number of such pairs is odd. Okay, because I am summing a certain number of odd numbers, so that will give me an odd number again. So this implies that X belongs to L prime, okay, because I have an odd number of certificates for that string x. Okay, any questions? Yeah, and also the proof of claim 6 is not very different in terms of idea. So there also you combine the certificates, but instead of looking at the number of certificates, you look at the probability. Okay, yeah, okay, okay. So what is happening here? So this says that the number of y1 that is good for my string x is odd. Okay, so now instead of L prime, if I look at the language L, so that means that, so now fix a y1. Okay, so suppose you have a fixed y1. So for a fixed x and a fixed y1, the number of y2s that is good for this x comma y1 is odd. Okay, so you have an odd number of y2s that is good for some y1. You move on to the next y1 again. You again have an odd number of y2s that is good for that y2. So I have a sum which is basically taken over an odd number of odd numbers. Okay, so therefore the resultant is also an odd number. I mean, I can just, so basically this last summation, this just means that I am combining all those certificates together. Okay, so again similarly, so let L be some language in C, L prime be pp dot L, and let L double prime be pp dot L prime. So x belongs to L. Okay, so here I cannot use, maybe I can, but I'll just look at one direction. So x belongs to L if the probability over a string z that sorry, x belongs to L double prime, that is what I want to show. That the no, x belongs to L prime, because this is acting as a certificate for x. So this pair y1 y2 is a certificate for x, and the number of such certificates that I have is an odd number. So this is giving me a parity machine for this language L. So I started with a parity machine for that, and I converted it into just one parity. So L prime of and this z1, x comma z1 is 1, occurs with, let us say, some probability 1 minus 2 to the power minus q1 of n. So this implies, so this is true if probability over some other string z2 L of x comma z1 comma z2 is equal to 1 happens with some probability greater than 1 minus 2 to the power minus q2 of n, and this is greater than one minus 2 to the power minus q1 of n. Okay. So now how do I combine these two random strings? Again by the same thing. So think of a string as a good string. Okay, so if it gives the correct answer for a given input. Okay, so suppose here I fix, okay, my x is already fixed. Suppose I fix a z1, the fraction of z2s that are good for x comma z1 is 1 minus, I mean this fraction of z2's are good, and the fraction of z1's that are good for x is this many. Okay. So therefore, if I look at the concatenation of these two strings, the fraction of the concatenated strings that are good for some x is how much? Product of the two probabilities. So it is greater than 1 minus 2 to the power minus q1 of n okay. So this I can just write this as 1 minus 2 to the power minus q1 of n minus 2 to the power minus q2 of n, and just ignore the last term since it's a positive term, and this is greater than 1 minus 2 to the power minus q3 of n for some polynomial q3. Okay. Okay. So the essential idea is same in both these claims. So let's look at the last claim, claim 7. Huh? Right. Yeah. So I left the other direction, but you can complete it. So it will be the same basically. I mean, the argument is the same. So if x does not belong to L, the fraction of z1's that are good is less than 2 to the power minus q1 of n. Then again you take the product, it will be less than something. So you can work that out.
X belongs to L double prime implies this thing, so x belongs to L prime. How does it like also? Why it is not x belongs to L? Because that is definition. And here?
Which one? This one or that one? Okay. Here, so what is happening here? So here I am saying that think of this as a random string. Okay. So the fraction of random string that are good for x, okay, so that acts as a positive evidence for x, okay, is at least this much. Okay. So what does that imply? So this implies that and this number we know that it is some polynomial q3. So if I just write down the definition of BP dot a complexity class C, x was where? So I had picked x from my language L double prime, sorry, L was my language in C. So therefore this means that x belongs to L prime, because that is the definition of BP dot L, right? It is a set of those strings for which I have a large fraction of random string which are positive evidences, right? And same with parity also.
So we could multiply the properties because they are independent?
Yeah, they are independent. Yeah. I mean, yeah, definitely in this case these two are independent events. Okay, so what is 7 is parity BPC is contained in BP.parity.C. So here, okay, so let me start the proof. So let L be a language in C. So then what is parity dot BP dot L is the set of all strings x such that the number of y's such that the probability over a random string z that L, X, Y, Z is equal to 1 is greater than one minus 2 to the power minus, let us say, q1 of n. Okay. So, the number of y's which makes this event happen is odd. So, let me just call this language L double prime, maybe I will need that. Okay. So, what we need to show is that L double prime is contained in BP dot parity dot C, and what we will show is something more stronger actually. We will show that L double prime is actually equal to this language, this L tilde, where L tilde is defined as set of all x's such that the probability over z that the number of y's such that L x y z is equal to 1 is odd. So, the probability of this event happening, that this number is odd, is greater than 1 minus 2 to the power minus q2 of n for some polynomial q2. Okay. So, we will appropriately fix our q1 and q2 later on, but essentially we will show that these two languages are the same. Okay. So, I mean, from the definition of L tilde, it clearly follows that L tilde is in which class? So, look at the definition of L tilde. So, with high probability, the number of y's, okay, which makes this predicate evaluate to 1 is odd. So, it is by definition in BP dot parity dot C. So, L was a language in C. Okay. So, let us define yeah, I will prove them equal, L double prime and L tilde.
So, why didn't you write it equal?
Yeah, so actually it is equal. So, when I had stated the claim last time, I did not realize, but actually yeah, these two classes are the same, because you can appropriately fix those polynomials, so that if you take any language here, it will be in here and vice versa. Yeah. But so the thing is that I do not think this is true for all complexity classes C. I mean, definitely it is true for the kind of classes that we are considering here, but I think if you have classes which are very large, okay, which looks at these kind of certificates which are exponentially long, probably there it will not work. So, when we look at the proof, we will realize that what kind of classes does this work for. Okay. So, define L prime based on L as the class BP dot L. Okay. So, BP dot L is set of all, I can think of them as tuples x comma y, such that the probability that L x y z is 1 is greater than 1 minus 2 to the power minus q1 of n. Okay. Okay, so let's look at a fixed x. So let's fix some string x. So we say that a random string z is bad for a string y if L xyz is not the same as L prime xy. Okay. So we have a fixed x. Okay. So we look at all the random strings z, and we try to see that when these two events, I mean if I think of them as predicates, when these two predicates do not give the same value. Okay. So if for some random string they give different value, I call that random string a bad random string. Okay. So what we know from our definition is that most random strings are good. Okay. For most random string, it does give me the correct value. I mean, it follows from the definition that a huge fraction is good, but there can be some bad strings as well. So the probability, just what I said right now, that if I fix a y, z is bad for y is how much? What is the probability that for a fixed y, my random string z is bad? Is less than 2 to the power minus q1 of n. Okay. So the probability that z is bad for some y is how much? So let's say we have let's say we know that our y has length L. Okay. So the total number of such strings is 2 to the power L. So the number of z's which are bad for some y is 2 to the power L times, okay, minus q1 of n, where L is the length of my y. Okay. So the probability that z is not bad for all strings y is basically the complement of this event. So this is greater than 1 minus 2 to the power L minus q1n. Okay. So again I can just write this as the probability that for all strings y, z is not bad, so which means that these two xyz is equal to L prime xy. Yeah, so I have the freedom of choosing what I want my q2 to be. So I'll set q2 to be what I want is that this probability should be and this entire probability should be greater than 1 minus 2 to the power minus q2 of n. So minus Q2 of n is equal to L minus Q1 of n. Will this work? Anyway, let us just not fix what our Q2 is, we will probably fix it later on. So I will just leave this blank for the time being, but let us see what we want. Correct, yeah. So the probability over a random string z that for all y's these two predicates give the same answer is so much. So if it happens for all y's, I can write this as probability over all z, parity of L x z is equal to the parity of L prime x. So what we have here is that for all y's these two predicates are the same. So more particularly their parities also should be the same. Okay. Yeah. So okay. So what do we have here? So what we have here is that for most z, that is with probability greater than 1 over 2 to the power L minus q n. So I had fixed an x. So this predicate is equal to this predicate, which means that, so what does this mean? BP dot parity dot L of a string x. Okay, so I just subsumed the probability in this operator. So this is equal to parity dot L prime, but L prime is nothing but, I think I erased it. Is it? No, so L prime is there, BP dot L. Okay. And this is what our L tilde was. Okay, and this was our L double prime. So we showed that this happens for a for any fixed x. In general, I mean this happens for all x's. Okay. So to put this BP operator, what I need is that this should be greater than whatever polynomial I want. I mean initially I wanted this to be minus q2 of n. So yeah. So q2 of n should be equal to q1 of n minus L. So that will work.
Why we didn't put BP in the right hand side also?
Because see, this predicate doesn't depend on the random string. So this predicate is true for all x's. I mean I just started off with an x, and this predicate is true for that x. Okay. So yeah, so the reason why I said that this might not be true for all classes C is because here I am assuming that my y has length L, which is some polynomial. Okay, I mean for this expression to make sense, this should be a polynomial. So if L is too large, so let us say if it is some exponentially large number, I mean I do not know whether things will work out fine. But as far as we are concerned, we are looking at the polynomial hierarchy. So all certificates have polynomial length, so life is fine. Yeah. Okay, so what have we seen? So we have seen these three claims. So So what remains of theorem 1 is lemma 4. Yes. Because, okay, so let me explain. So what does this mean? So I started off with an x. Okay. So what this means is that yeah, maybe this is not a correct notation. Yeah, I should not use. I mean, I wanted to use x because I wanted to show this for a fixed string, but I think together with x I should also use the random string that is generated by BP and the y that is generated by this parity operator. So what this essentially means is that with high probability, okay, so if you look at all random strings, for most random strings, the number of y's, okay, that will act as an evidence that x belongs to the language is odd. Okay. So yeah, so notationally, yeah, I mean I can erase this and rephrase this in English, but I mean as long as the idea is clear, I think it should be fine. This one, I mean this follows from the definition, right? So L prime was BP dot L, right? So I am just adding the parity operator to it. So for an odd number of y's that happens. So what this meant here was that for an odd number of y's, x belong to L prime, okay, such that x comma z belongs to L, and x belongs to L prime if there is some z, I mean if there is a large fraction of z which acts as an evidence. Yeah, so think about it. So there is nothing very intricate happening here, but think about it. Okay. Okay. So again, here what we will assume is that C is not just any complexity class, but it is some class in the polynomial hierarchy. Okay. So what we will show is that there exists C is contained in BP dot parity dot C, where C is equal to sigma IP for some I greater than 0. Okay. So for any I greater than 0, we will show that it is true, and that will be sufficient. So this proof is quite easy. I mean once we assume that we know how Valiant-Vazirani works. So what this means is that okay, so let L be a language in there exists C. So this implies that there exists some L in C such that there exists, oh sorry, there is some L prime in C such that L is equal to there exists dot L.
Why is a polynomial that L should be a polynomial?
L should be a polynomial. So that is why I said that I mean we should be fine as long as we look at classes where the certificates are of polynomial length, and since we are dealing within the polynomial hierarchy, I mean everything is fine. But so maybe it also works for higher classes, I am not quite sure, but I doubt it. Yeah, this proof will not work, maybe something else will work. So yeah, so X is in L implies that there exists some string Y such that X comma Y is in L bar. So that is the definition. So now if I apply Valiant-Vazirani to this, what I can say is that this is true if, I mean if this is true, then with high probability, if I pick an appropriate hash function, okay, so here my y is the certificate, okay, so think of it as the satisfying assignment of the formula x. So with high probability, if I pick a hash function h, then the probability that x comma y, okay, that the number of certificates y such that x comma y belongs to L prime and h of y gives me the all zeros vector is 1, with probability greater than 1 over A10. Okay. So again we can think of that set T. I mean if you look at the main theorem that we proved for Whaley and Vazirani, we can always look at an abstract set of certificates, okay, which has size between 2 to the power k and 2 to the power k plus 1, then this holds. Okay, so all we need to show is that this computation, this entire computation can again be done by an algorithm which is in C. So of course the first part can be done by an algorithm which is in the class C. The claim is that the second part also can be done by an algorithm which is in C, because what this is essentially doing is this is taking a hash function which has some very nice form. I mean it is not some arbitrary function, and it is just evaluating a string on that function, okay, and checking if that equals the all zeros. So I can just write this as the probability over h of some L tilde x comma the number of y's such that L tilde of x comma y comma h evaluates to 1 with probability 1 over A10. Okay. So now again, so this is if x belongs to L, and if x does not belong to L, what we know is that for all y x comma y does not belong to L prime. So with, if I again take the same machine L tilde, this will evaluate to 0 on all such pairs, okay, because the moment I am taking this and for all y's this does not belong to L prime, so this predicate always evaluates to false. So therefore the probability that the number of y's such that L tilde x y h is 1 is 1 is 0. Okay. Now again we can, since this is a one-sided error machine, I can take some polynomially many trials and amplify our success probability so that this becomes a BP machine. So take so just state this some polynomially trials to show that L is in BP dot parity dot C. So once again, I have stated this as just one solution, but you can interpret this as an odd number of solution, okay, because of course if I take many trials, this property will not be preserved, but what we know will be preserved is the parity of the number of certificates. So if this has an odd number of certificates, I can always construct a proper language, an appropriate language, which will belong to parity dot C. Okay. Yes. So again, what I advise is that as an exercise for today is you so you try out all the proofs yourself. Okay, so they are not difficult proofs, but once you try them out, it will make you more confident. Okay, so I'll stop here today. So what we have is we have lemma 4 as well. So what remains to be seen now is why BP dot parity dot P is in P to the sharp P. So that will prove Toda's theorem.